Hello, check, 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 one, two, check, one, two,
Very good afternoon to all of you. Before I set the stage for today's talk, uh, let me, for the benefit of many people who are for the first time attending the Foundation Day, uh, let me tell you why 6th September is Niger's Foundation Day. We have a very curious story of, some of our colleagues were just discussing a while ago. It's a very curious case of Foundation Days. Uh, like many of us, Niger also has a couple of birthdays. That reminds me of a biologist turned sociologist, Herbert Spencer, who gave this classical theory of organic analogy, wherein he drew an analogy between social systems and human body. So, like human beings, social institutions, systems also burn. So they burn, they mature, and they decay. So talking of birth and birthdays, many of us, I'm sure, many of us, as in many people of my generation or older, would probably have 2 or 3 birthdays. One would be the day of birth, one would be a tithi wala, and the other one would be possibly a certificate wala, क्योंकि उस समय याद ही नहीं रहता था. जो टीचर 10th सर्टिफिकेट में लिख दे वो बर्थडे हो गया. So many of us, I know for a fact, I'm sure many of us would have a couple of birthdays. So similarly, Niger has, we used to, when we started celebrating the Foundation Day, 29th December was the Foundation Day because that coincided with a milestone event. Then later on, we realized that the attendance for Foundation Day on a 29th December would obviously be very, very poor, primarily because it's a break time and it's between Xmas and New Year. So I don't know, 6th September, whether it helped or not, but it certainly helped in a way that we at least have a working day to celebrate this day. So 6th September is the day on which the academic program formally started from the transit campus and IOP campus. So that's how when Niger policymakers or when people at the helm of the affairs thought of changing, 6th September was chosen as the foundation day. So today is the 15th birthday of Niger. Talking of birthdays, I'm sure we all celebrate a birthday with a lot of festivity and fervor. So the foundation day of an institute or institution should also be celebrated as we do on our birthdays. As a convention, we invite people of eminence to deliver this foundation day lecture. So before I introduce today's speaker to all of you, let me invite Professor Hirendranath Ghosh, the director of NISER, to escort our chief guest to the dais. A big round of applause, please. Can we have a flower bouquet for both the dignitaries on the dais? Professor Ravi Bhushan Grover, doesn't actually need an introduction to an institute which is under the aegis of the Department of Atomic Energy and also an OCC of Homeover National Institute. However, he deserves a long one. So let me try to do justice to the name. Professor Ravi Grover is an Indian nuclear scientist and a mechanical engineer. He uh, was the founder vice chancellor of HPNI. When it started, the designation was actually director, not vice chancellor, if I'm not wrong. But going with the changing nomenclature, it was later changed to vice chancellor. Professor Grover is a mechanical engineer by training and a nuclear scientist by profession. He graduated from the Delhi College of Engineering, the one which is called Delhi Technological University now, with a mechanical engineering degree. And he did his PhD from the Indian Institute of Science, Bangalore, in the year 1982. Post that, he joined BARC, and he has served BRC in several capacities, which include the director of the Knowledge Management Group, the associate director of Technical Coordination and International Relation Group. He also represented BRC at various international forums, including the World Nuclear University. His professional career also includes a member of the Atomic Energy Commission, which he is currently now, the chairman of the Board of Research in Nuclear Sciences, the fellow of Indian National Academy of Engineering, and the World Academy of Arts and Science, president of Indian Society of Heat and Mass Transfer. He's been awarded one of the highest civilian awards by the government of India, Padma Shri, in the year 2014 for his contribution to nuclear energy. Many of his, his illustrious career has a lot of other awards, including Distinguished Alumnus Awards from DCE, Distinguished Alumnus Award by Indian Institute of Science. In Delhi, in 2016, DCE also bestowed him with a Lifetime Achievement Award. During his first 25 years of career, Professor Grover worked as a nuclear engineer and specialized with specializations in thermal hydraulics. On 15 January 2013, the Prime Minister of India, the then Prime Minister of India, conferred on him the Lifetime Achievement Award for the year 2011 for his outstanding contribution in the field of nuclear engineering towards the national initiative to open international civil nuclear trade for the development of the framework of governance of nuclear power and human resource development. The citation of the award states, during a career spanning 4 decades, Dr. Grover has distinguished himself as an academic, research and development engineer, and a science administrator. His knowledge of nuclear engineering and nuclear law has earned him this title of nuclear diplomat. The citation also says he played maximum role in all steps taken by the government of India towards opening international civil nuclear trade. He played a lead role in setting up HPNI, which goes almost without saying. He was the head of HPNI from its inception in 2005 till 2016. And I would not be wrong if I say that he has brought single-handedly HPNI to the stage and it is right now as one of the leading research universities in the country. That reflects in the NIRF ranking as well. So I do not think we could have had a better speaker for the day than Professor Grover. If you have questions to answer, if you have questions related to strategies followed by India in providing trained manpower for nuclear industry, development of nuclear energy programs and the role of government, whether nuclear energy could be a response to energy and climate in India, to know about Indian experience in the capacity building as a part of development of atomic energy program, technology and knowledge management in and by the Department of Department of Atomic Energy. If you want to understand the scenario of growth of energy mix in India, nuclear power and sustainable development, prospects of nuclear energy both in India and internationally, several policy initiatives, if you want to know about the government on acceleration of installed nuclear power capacity in future, here is the man right in front of you. So I would not take further. to stand between you and Professor Grover. A huge round of applause for Professor Grover.
Good morning, and thank you, Pranay, for that kind introduction. Professor Ghosh and distinguished faculty and dear students, energy transition is a very important topic these days. The number of programs you see on TV channels and number of inch spaces in print media which is being devoted to this topic is really increasing. So today I'll talk to you about transition, but why development-led transition? Why this suffix there? In place of development-led transition, one can have transition-led development. And I think you can clearly see the difference between these two. As a developing country, we have to give primacy to development. Of course, transition has to be in focus at the same time. But moment you think in terms of transition-led development, development becomes secondary, which a country like India really cannot afford. So that's why the title here is Development-led Transition to a Net Zero Energy Mix in India. Again, I've used energy mix and not electricity mix. As you know, there is a difference between energy and electricity. Electricity today in India is about, I think, 22% of the final energy consumption. So we are talking of energy mix as a whole. And while this term is conventionally used, energy mix, I think when we want net zero, we are talking of something more than that. In certain industrial processes, let's say a blast furnace, where we then reduce iron oxide to iron, carbon is used as a source of energy for the reaction to take place. It's also used as a molecule for reducing oxide to iron. That also leads finally to emission of carbon dioxide, and one has to find a substitute there as well. In a similar manner, in the production of fertilizers, we use syngas, where ammonia is used, and this ammonia or hydrogen, which is later on converted to ammonia, comes from natural gas. There again, we have to find a substitute for that if we want to aim at net zero. So net zero has to be looked at not only for electricity, it has to be looked at from the point of view of energy mix as a whole, and also wherever we are using certain molecules which are derived from fossil fuels for industrial purposes, there again we have to find substitute where there is no emission of carbon dioxide or any other greenhouse gas. So with this background about the title, let me proceed further. And first point, we have to see how exactly global energy consumption has grown over the years. Here on the x-axis, I'm starting from year 1800. Existence of coal has been always known to man, I think right from the year 600 of Common Era onwards. But it was very difficult to mine coal, so it was not being used extensively. Why it was difficult to mine coal? Because mine used to get flooded with water, so mining was a very risky business. Around 1700, I think to be precise, 1698, a steam-driven mine dewatering pump was developed. Now, with that development, mining became safer. So miners started mining coal more and more, and the usage of coal increased very slowly. And from 1800 onwards, its increase started and accelerated around 1850 and move on. You see how much coal is being used today. And before that, most of energy was derived from biomass. And notice one point, and I'll come to this later again, that biomass usage is remaining almost same as earlier. It is still being used extensively by large section of population, particularly for cooking. And this has an implication. So here, earlier it was before this year, 1800, it was almost entirely biomass and muscle power of human beings, muscle power of animals, which was providing energy for mankind. But then situation changed and fossil fuels came in, and now you can see in 2023 how much we are getting from coal, from oil, from natural gas, from nuclear, hydro, wind, solar, modern biofuels, renewables, and others. So this is the current situation, and we also see to what kind of energy usage, to what extent energy use has grown over the years, and all this has happened in last 2 centuries. So first grand energy transition, as one can call it, transition from muscle power and biomass to fossil fuel started in 1800, and now we are in 2023. So with this background, let us have some observations about the current era in which we are living. Current levels of energy use, as we have seen in the previous projection, is very large. It is so large that it underpins numerous existential threats. Threats include environmental disasters which are happening all around because of rising temperature, the way weather is being impacted. So ecological crisis is the first one. The resources will become scarce and scarce as we continue to increase the use of energy over the years. And most importantly, it is resulting into geopolitical instabilities. When a particular item is coveted very much by all, everyone wants to acquire that item. You see, the Gulf region, which has petroleum reserves and plenty of them, has been always a region of instability, political instability, because all the multinationals want to acquire that resource, and all sorts of things happening in that region, and it has been going on for right from the time when petroleum was first discovered. But though we see all these threats, whether ecological or resource scarcity or political instability, consumption of energy is continuously rising. Why? Because aspirations of human beings are rising. All of us want more and more of energy, the way our lifestyle is evolving at the moment. So But when this greenhouse gases, with the carbon dioxide and some methane and some nitrous oxide, they get released, the result is it's resulting into global warming. If there was no carbon dioxide, no methane, no nitrous oxide, planet surface would be frozen at minus 18 degrees centigrade, because we have some amount of these gases in the atmosphere, and they absorb some infrared radiation which comes out of Earth, and they keep the mean temperature of the troposphere at about 15 degrees centigrade. In India, it is higher, some places it is lower, but global mean is at 15 degrees. But if their concentration increases, this global mean will increase, and that is what is climate threat, about which we are reading a lot in the both in the print media as well as on TV channels. There have been, ever since industrial revolution started, we started using energy. Energy efficiency has been increasing, and as a result, productivity has increased, and increased productivity has led to further growth. And global energy usage has been continuously increasing, but there have been isolated times when energy doesn't increase. If we see in this century, the first was in 2008, when there was an economic crisis led by the collapse of banking system in USA. There was a slight dip in energy usage. Second, in this century dip was when COVID happened. Again, that temporary dip. But these dips are temporary. Their effect lasts 1 year, 2 years, and again energy usage starts increasing. But there is a very interesting fact when happens when anything becomes more competitive. It's a human nature, we tend to use it more. Economists call it rebound effect. You see, we know that LED lights consume less energy, but what's happening? The usage of LED lighting has increased so much that if you compare wattage of lighting in a room, wattage will perhaps same or more than when it was earlier. In a typical drawing room in a middle class family, earlier there used to be one tube light. Now you will have 6 surface lights there, and total wattage will be more than what it was earlier. When usage of domestic refrigerators started in India in 1970s, everybody used to buy 165-liter refrigerators. Now all of us think in terms of 300, 350, 400 liters refrigerators. And I think now double-door refrigerators also have come in the market, and very soon people will move towards that. And this you can go on, and it happens in all commodities, whether food items or clothing, and it's also happening in terms of for those items where energy is used. So this rebound effect also is happening at the same time as we are concerned about energy usage. I think there's a narrative which has been made popular by developed world, that they have been able to decouple economic activity from energy usage, that they are able to increase higher levels of GDP, higher level of human development index without concurrent increase in energy usage. But this narrative has a hidden fact. And that hidden fact is that they are using certain accounting conventions. Now, if a developed country in European Union or North America, they use steel, rather than producing themselves, they are importing it from India and China and other countries. Usage is still there only, but energy is being used in China or India. So this accounting convention, which is based on production-based methodology rather than consumption-based methodology, is creating a feeling that, oh, they have decoupled economic activity from energy use. Moment you replace, add energy embedded in the steel which is imported, steel or other products which are imported to USA or Europe, this scenario changes. You will hear from many people within India, look, Kerala has been able to achieve a very good level of human development index without high level of energy consumption. But there's again a hidden point here. 35% of Kerala's GDP is because of remittances. The dollars which are earned by them, Keralites, whatever is Keralites, it is applicable to all other people who are remitting and funding home. Those energies used there, but benefit is coming to Kerala or wherever those remittances come in. So this we have to remember that moment you think in terms of change these accounting conventions, scenario changes, there has been energy efficiency improvements, yes, but decoupling, total decoupling of economic activity from energy use has not happened, and it is not likely to happen in near future. So one thing which we noticed from the previous projection, that the first grand energy transition, which replaced muscle power and wood with fossil fuels, has taken 200 years, but it is still not complete. There is a considerable use of biomass. If you see energy terms, it is about 6% of energy is still by biomass, 94% coming from fossil fuels and other fossil fuels, nuclear, hydro, etc. But it hides one fact, that 6%, 1/3 of human population, by about say 500 million in India itself, they depend on biomass for cooking. So if you look in terms of percentage of exajoules or kilowatt hours, it is 94%. But if you look in terms of how many human beings are influenced, how many human beings are still using biomass, which is something not good to use, it is 1/3 of human population. Why it is not good? Because biomass is used in basically kitchens for cooking, and particulate matters which is emitted by biomass is inhaled by women and children who spend more time in kitchen, and the result of that inhalation is that children, young children, women who spend time in kitchen, they suffer from respiratory ailments. So this point, and now when that first grand transition is still underway, we have started calling for decarbonizing economy, that is second grand energy transition. So here you notice that in this energy transition, several issues, health, social science, technology science, they are all intertwined. So one cannot look at this kind of issue with disciplinary boundaries. One has to have a global picture on this, and this will become clear as we proceed further. And we must always remember that disciplinary boundaries have been created by us for the facilitation of education. Actual problem, real life problems do not honor disciplinary boundaries. They are always spanning various disciplines, and they are not confined to only science or only technology. They cover science, technology, and social sciences, all disciplines. So if we want to decarbonize, the first thing which we have to do, we have to identify those energy sources which do not emit the carbon dioxide. This is data from a 2022 publication, life cycle GHG emission, greenhouse gas emissions, in terms of carbon dioxide equivalent per kilowatt hour. So first one is pulverized coal without carbon capture. This horizontal blue line is the median value, and this you can see this is very high. So is with IGCC without CCS. This is supercritical boilers without CCS and natural gas, and then with CCS from values close to 1000, we are able to come down significantly, but still it is very high. But when we go this side, where we have hydro, nuclear, concentrated solar power, photovoltaic, then it becomes very low. Then wind. So basically, we now have to use more and more wind, photovoltaic, concentrated solar power, nuclear, and hydro if we want to decarbonize. This is what this data tells us. This data is for various regions. The regions are listed here at the end. For example, this is Japan, this is India, Latin America, Middle East, and so on, various regions. But that is not important. Important point is this blue lines, which is the median value, and which tells us where exactly the greenhouse gas emissions are low. So, with this background now, when we talk about decarbonization, economy-wide decarbonization, what it will look like. So, carbon dioxide is emitted by several human activities, including energy services like electricity, which we use, and industry and agriculture. In modern civilization, they use 4 materials which really contribute a lot to greenhouse gas emissions, and these materials are ammonia. Ammonia is used extensively because ammonia is used for production of fertilizers, and it is because of the use of fertilizers that agricultural productivity has grown up so much in the last 100 years. Steel, again, blast furnace, we reduce ferrous oxide to Fe, and again, the result is use of carbon for heat generation, use of carbon for reduction, steel, the cement, and plastics. All this use, there are more material we use, but these 4 materials are really pillars of modern civilization, and all of them result in production of carbon dioxide. So now what we have to do, we have seen what are the low carbon sources. Rather than using petroleum products or coal, we have to use low carbon sources like hydro, nuclear, solar, and wind. Now, hydro, nuclear, and solar and wind, these sources provide you electricity. So how do we, what do we use in the industry, whether it's the steel industry or whether it's fertilizer industry? So we have to use electrified products, means we have to first generate electricity and produce products with the help of which we can carry out those reactions or those industrial production as it was earlier. And that can be done only if we use electricity in electrolyzers to produce hydrogen, and then use hydrogen for carrying out, doing the same job as carbon as a molecule is doing. And in case of ammonia, we can use carbon for synthesizing ammonia, and then use ammonia for producing fertilizers. There are some areas where it's very easy to decarbonize. For example, transportation, electrical vehicles, light duty transportation. One can easily use electrical vehicles. Space conditioning. In India, we use only air conditioners which run on electricity, but in the West, they are using heaters in winter, either natural gas or electrical heaters. They have to now use heat pumps in place of whatever they were using earlier. Lighting, switch to LED lighting, and that is where we are able to proceed further. So technologies are available, but now we have to invest capital to decarbonize, and that capital investment is not a one-time affair. It will take quite a few decades to get that much of capital and invest that. But there are certain processes or certain activities where it is difficult to eliminate carbon emissions. Aviation is one, which is using petroleum products, aviation fuel, how to replace that, what to do there. Long distance transport, should we have batteries or should we do something else there? Shipping. So these areas are difficult because these areas, aviation and shipping in particular, there will be always a competition between revenue cargo space and onboard batteries. We cannot have too many onboard batteries because the revenue cargo space will become less. So this is area where various alternatives are have been proposed, and still one cannot say final word as to which direction one will move. Then production of carbon intensive materials like steel and cement is another difficult area. For example, let us say steel, the current practices, the way furnaces are designed, the way processes are carried out, they have evolved over several decades of development work. Now, replacing carbon with the hydrogen will mean that that development process has to be redone because the industry is bothered about the product quality. Product quality will depend upon how the whole process is carried out. So that cannot happen just by lab scale you do something, but when you go to industry, those processes have to be handled at a larger scale, and many things we observe during practice, and this evolution is a continuing process. Then also there is one more aspect, the way we have structured our life, we need electricity 24/7, but solar and wind are intermittent sources. How do you take care of the reliability aspect? Electricity has to be always available to you, and if supposing at night time you are dependent on solar and wind only and wind is not blowing, what do you do? So one has to go for storage and try to see how exactly then use of hydrogen and energy storage, they are the one who will hold the key, and we'll come back to this later. But in spite of all this, fossil fuels cannot be eliminated. Some residual emissions will always be there, particularly in industries like cement, where you are trying to convert calcium carbonate to calcium oxide, carbon dioxide will be emitted. So you have to have some method for carbon capture, its use and sequestration. So there's a lot of R&D which has to be done by chemists here. They have demonstrated on lab scale about carbon capture, use and storage, but now it has to be demonstrated at industrial scale, and that's a lot of development which has to take place. So earlier when we were thinking about electricity system, we were thinking a system like this, where we have generating station at one end, step up transformer, transmission lines, step down transformer, and various customers. This is a simple system. This is the one which one was looking at, but now the whole scenario changes. We will have various generators. We have nuclear power plants, we have fossil fuels with carbon capture, we'll have renewables like solar and wind. We also have biomass power plants with carbon capture, and they will feed to the grid. Whatever carbon is captured from this will come to industry, and here the power from the grid, it will go to consumers, but it will also go to water electrolysis plant and storage, and this hydrogen will also go to industry, and this residential, commercial and industrial centers will be using the industry. So we have to now look at the entire picture in an integrated manner. Of course, the research and development will continue. There could be tomorrow new methods of new technology, for example, hyperloop for more efficient transport or more efficient electrolyzers, and there can be even more methods of generation. So this system now becomes much more complex. Optimization studies have to be carried out on this system rather than on what was being done earlier. So as we proceed further, the issue arises, how much energy will India need? Now here I think you will find various estimates, and there are top-down approaches, there are bottom-up approaches. In bottom-up approaches, they identify what are the various dimensions on which energy is used. For example, you need housing. And for housing means you need cement, you need all the construction material. So what area of a house a person will need? How much square meter of space a person needs? Based on that, clothing, washing machines, all these activities, they assume that and then try to calculate the uh, energy requirement for decent living. But this approach suffers from one flaw. One person may think that a one-room kitchen is sufficient for a family. The other will say two-room kitchen, or the third will say three-room kitchen. And I find this kind of bottom-up approaches people have used, but there's a wide disparity of uh, forecast by these people. But if you use a top-down approach, simple, have a human development index on y-axis and final energy consumption on x-axis here. And one finds that these are the various countries. All these red dots are about above a HDI of 0.9. And but for this one outlier, we find that no country has been able to achieve a HDI of 0.9 lower than 75 gigajoules per capita per annum. So this tells us the minimum which is needed. This outlier is Hong Kong. Again, I said accounting convention is the reason here. They import everything. All their income comes from financial services, banking services. They are a hub for financial services. They don't have manufacturing. They don't have agriculture. They are importing everything. So that cannot be a role model for India. We have to think that if we want to have a SDI of 0.9, we have to think in terms of 75. Now, when different people forecast, somebody will say, okay, why India should go to 0.9? India should be happy with 0.7. Immediately forecast is lower. So these are the various think tanks, depending upon what is the thinking, they are coming up with various forecasts. And my argument is that we are a member of G20. Australia, Canada, France, Germany, Japan, South Korea, UK, USA, they all have SDI of 0.9. Once we say that, we claim that we want to become Viksit Bharat by 2047, we are a proud member of G20, we should also have a HDI of 0.9 or above. So that means we should, if business as usual, we should think in terms of 75 gigajoules per capita per annum. If we do that, so where do we end up? First one, we have to electrify all end uses and use electrified inputs for industrial processes. That can be the only way forward. Business as usual means we need 75 gigajoules per capita per annum, and assuming population by 2070 will stabilize at 1.5 billion. It is expected that population in India will peak around 2050, and after that it will start decreasing. So we just, for the sake of argument, we assume 1.5 billion population, 75 gigajoules, and then conversion factor usual, we come with the estimate of about 31,000 terawatt hour per annum. That is energy requirement for India. It's a huge, large amount. Then one can develop scenarios, assume energy efficiency, assume we'll be doing certain more things locally rather than importing photovoltaic cell. We'll be producing them in the country where the current stress on made in India is there. Then with this exercise, we develop various scenarios. Then this 31,000 reduces to 23,000 to 27,000 for various scenarios. In per capita terms, it comes to 15,000 to 18,000. And one can choose a benchmark for further arguments in this range of 50,000 to 18,000. Then we thought, okay, let us choose 16,000. So 16,000 multiplied by 1.5 billion, it gives us 24,000 terawatt hour of energy generation. And a part of it, roughly 60% or so, will be used as electricity. Remaining 40% will be used in electrolyzers for producing hydrogen. And that, this is the requirement to become, to reach net zero and become Viksit Bharat. Where are we today? So we see the important data. This data is published by Ministry of Statistics and program implementation every year. They come out in the month of March, a publication called Energy Statistics. And their latest energy statistics tells us that total primary energy supply is 9,890 terawatt hour, and final energy consumption is 6,415 terawatt hour. Now, earlier one was always quoting in terms of total primary energy supply when petroleum and coal were the major energy supplier, because when you convert coal to electricity, efficiency of 33% or so comes in. Modern plants are more efficient, going to 41%, 45%. But now we are mixing renewables, which produce electricity, with fossil fuels, which give primary energy. So energy economists have started using a term final energy consumption. At the point where energy is used, that is where they are used. So this report this does give data in terms of final energy consumption in India. In the fiscal year 22-23, it was 6,415, and just this one has to remember. I'll come back to this number further. Out of this, electricity consumption was 1,400. Roughly 22% is electricity consumption. Now we have to electrify everything. So this tells us the journey which we have to travel. So during the decade 13-14 to 22-23, compound annual growth rate for electricity generation was 5.13%. Generation in 22-20, oh, this should be 22-23 here, was 1844. This is consumption, and this is generation. In between there are losses. So, and this has increased to 1980 in 23-24. If we keep CAGR continues to be 5.13%, we'll be able to reach our goal by 2070. Only thing is we have to keep growing at 5% or above 5% from now till 2070. And demand continues to increase. It's only I sometimes feel that whatever today we are forecasting, we may need more, because several new usages of energy are coming. We are having data centers, artificial intelligence is consuming a lot of energy. Then certain things like, for example, theme parks, which are being established in all cities, they also consume a lot of electricity. All these new applications are emerging, and what new application will emerge from a decade from now, we do not know. So again, I repeat what I have said earlier. Many have given lower forecasts, but their target is HDI of 0.8 or even lower. And they assume things like that India will not need any air conditioning. It's a tropical country, will be able to proceed like this. But I think that is not happening. We will need more energy. So now when we see various sources of energy, where from we will get it? So there, to know about that, first we have to see what is the land use intensity of electricity generation methods. For every generator, we will need certain land. Here, this is from a very publication about a year old. Nuclear, you need 7.1 hectare per terawatt hour per year. Geothermal 45, wind 130, biomass residue. Residual biomass means from after agricultural operations, whatever is left unused. It is 130. But moment you have dedicated energy crops, it becomes 58,000. This difference one has to note. Natural gas 410. Natural gas footprint of where the plant is. If you see piping which it interconnects the entire thing, this becomes more along. If we take that spacing also, it becomes 1900. Hydroelectric single purpose dams. In case of multi-purpose dams, one will say that one is using those water for irrigation and so many things. For single purpose dams, it is 650, coal 1000, concentrated solar power 1300. The natural gas spacing I have already indicated. Ground mounted photovoltaic cell 2000. Windmills with spacing, you have to space, it becomes 12,000. And biomass dedicated based on energy crops, 58,000. And along with this, we have to see density of population in India. And then we'll know the solutions which are acceptable to countries where density of population is low, like Canada, Russia, Argentina, Brazil, USA, are not applicable to India, where our density of population is many times that density of population. So we have to find solutions which are specific to India, considering our density of population, considering land use intensity of various generation sources. So based on all this, first let us see what is the generating potential of renewable sources. There is a very good publication, which is, I think, first of this kind on this topic in 2012, where all sources of renewable energy have been looked at, have been examined. And the author argues that the total electricity generated could range between 1800 to 5800 terawatt hour. And compare this with our current energy consumption itself is more than 5800. And this is what is the total potential of renewable sources. Our estimate, which we have recently done, is about 5,490 terawatt hours. Of course, it can be increased if tomorrow efficiency of photovoltaic cells increase. This will be increasing. Already this particular, for wind energy, it has been assumed that certain mast height has to be assumed. Earlier, initially windmills were being installed at a mast height of 50 meters, then it became 80 meters, then it became 120 meters, and now one is thinking in terms of 150 meters, and this estimate assumed that the mast height of windmills is 150 meters, the maximum which we have been currently able to assume. And in case of photovoltaic cell, one needs land area, and perhaps many of you may be knowing that we have an institute of remote sensing. They, based on satellite picture, they map land mass of India, and there's a ninefold classification which government has come up, what kind of land it is. And from there, the government has, Ministry of MNRE, Non and Renewable Energy Sources, has come up how much land maximum can be devoted to photovoltaic cell. We need land for residencies, we need lands for highways, we need land for agriculture. Certain percentage, only very small percentage, can be devoted to photovoltaic cell, and based on that, this estimate has been arrived. So this is the total potential, and 5,490 is less than what we currently are consuming. So what it means is that we have to develop all low carbon technologies based on a technology agnostic framework. We only say we need low carbon electricity generation. Since, I mean, advocating that we use only renewables is not the answer. We will not be able to become a developed country if we concentrate on the fact that our potential of renewable energy is very low. We need renewable energy, we need nuclear energy, we need coal with carbon capture. If you see, go about 1 year back, government was saying we will not establish any more coal plants. But this year, in the speech by Finance Minister Nirmala Sitharaman, she came up with, yes, we'll even go for advanced technology for coal generation. Ultra high supercritical power plant technology has been developed in India, and she specifically named that plants will be established. CEA has come up with estimates where they have set some 7 or 8 large coal plants will be set up. So I think after this realization, I think this has taken hammering by several of us, that we cannot become a developed country if we say phase out coal. We have to continue to develop, and for that we need energy. So India must nurture all technologies which are likely to contribute to goal of economy-wide decarbonization. And one thing which we have to remember, all of you are aware of this, that whenever we have a power-to-power conversion, that is, we convert electricity to hydrogen in an electrolyzer, it's not 100% efficient. The efficiency will be always less than 100%. Then you convert hydrogen back to electricity, again that's less than 100%. So wherever we can use electricity directly, we should do that. Wherever it is not possible, we think in terms of conversion. The conversion is less than 100% efficient. This also one has to remember. I think I can cite several examples, but I will not go into examples. Well, still a part of electricity we have to convert to hydrogen because that is needed. Hydrogen will be needed as molecule in producing ammonia, in converting iron oxide to iron. So that conversion will become a must. But wherever possible, use electricity directly. So where are we with respect to nuclear technologies and uranium availability? Present installed capacity about 7.5 gigawatts. The nuclear power plants are working at the 7 sites, that is Tarapur in Maharashtra, close to Mumbai, Rawat Bhata in Rajasthan, Kalpakkam in Tamil Nadu, Narora in Uttar Pradesh, Kakrapar in Gujarat, Kaiga in Karnataka, and Kudankulam again in Tamil Nadu. Around 47,000 or 48,000 terawatt hour generated in 23-24. The current technology, which is plant which are being installed by Nuclear Power Corporation of India Limited, they are all 700 megawatt rating pressurized heavy water reactor. Kakrapar 3 and 4 units are already working, and 14 units of 700 megawatt rating are at various stages of construction and planning. 2 more units of 700 megawatt are about to be commissioned. They are in Rawat Bhata in Rajasthan, 2 in Haryana, and 10 in various other places are being implemented. We need uranium to fuel these reactors, and uranium is not available in the required amount in India. Whatever is available, we are mining it, we are converting that to fuel, but that quantity is not enough. So now India is as a country has a unique status globally, unique status because India is a country which has not signed the Treaty for Non-Proliferation of Nuclear Weapons and has a live nuclear weapon program. So a country like this, earlier India was not allowed to participate in civil nuclear trade after negotiation which went on for a long time. Now that has become possible from 2008. We are able to import uranium. Our program was kind of at a standstill. We were not able to proceed further because uranium was not available in the country and we were not able to import uranium from international market. After 2008, situation has changed. We are importing uranium. And as I said earlier, we have many reactors now under construction. Again, spent when in a pressurized heavy water reactor, when we burn uranium, we do not use entire uranium-235 there. Uranium-238 get converted to plutonium-239, and one can reprocess that fuel to recover plutonium, and that plutonium can be used in fast breeder reactor, and recycling technologies have been developed in India. Recycling plants are working at their nameplate capacity, and the next generation of reactors, that is fast breeder reactors, have been developed. First reactor, which is prototype, has been completed in Kalpakkam. At the moment, fuel loading is going on. One expects it to achieve criticality within this year. And apart from 700 megawatt reactors which are under construction, 4 light water reactors are under construction at Kudankulam in technical cooperation with the Russian Federation. Again, industry is looking for captive power plants, industry like steel and aluminum industry in particular. Steel, aluminum, steel and also fertilizer, railways. So for that, government has announced that 220 megawatt reactor, pressurized heavy water reactor, which we have plenty. It's a live design. We'll call it Bharat small reactor. Its design is incrementally improved, and then some business model is being worked out so that it can be kept, private industry can be allowed to use it as captive power plant, but this is a work in progress. Progress as the technical part is very clear to NPCIL, but what kind of model it will be, business model it is going to be, which has to be within the legal framework, that work is currently going on. Well, so the way forward, I think we need energy for development. We have to electrify and use services and use electrified products for industrial processes. We have to deploy all low carbon sources, that is hydro, nuclear, solar, and wind, to their full potential. For the balance, use fossil fuels with carbon capture, and carbon capture technologies have to be developed. We have to move out of lab now to industrial level. To ensure energy security, we have to encourage localization of supply chains. The fact that in case of solar, supply chain is not within India, it's a matter of concern. For hydro, nuclear, and wind, we have supply chain sufficient within India. And we have to pay due attention to all elements in the system and system integration. The last system which I showed you earlier, involving storage, involving hydrogen generation, that whole system has to be optimized by using optimization techniques. We did one exercise that currently we in India and even elsewhere, storage and hydrogen generation are being looked in a disaggregated manner. If we look at them in an aggregated manner, that means whenever we have surplus electricity, load will keep fluctuating, generation will fluctuate because of intermittency, you run electrolyzers. And whenever more electricity is needed, let the supply electricity as per the demand. If you do that way in a synergistic manner, you can minimize both capital expenditure and operating expenditure. But unfortunately, we are looking hydrogen generation and storage in two different silos, and this kind of stovepipe approach is not going to work. But I have been trying to give this message in every talk, wherever I give, in policy planning circle, everywhere. Somehow this message seems to be going forward. I hope there will be symbiosis soon between electricity and hydrogen as energy carriers. And then I must say that we must use science-based definitions, such as low carbon hydrogen rather than green hydrogen. Green doesn't convey anything. Calculate over the life cycle how much carbon is being produced and use science-based definition, and some countries have gone in for that. So this color, brown hydrogen, green hydrogen, pink hydrogen, these colors are no good to convey. Use science-based definitions. Base policies on credible science and engineering. Don't go by just business lobbies. Look at credible science and engineering in everything you speak. And there are certain technologies which today are speculative or futuristic. You can, I will like to use work futuristic, some call them speculative, but today they may be speculative or futuristic. We have to work to convert them to credible technologies. And that is where research in institutions like this is very important. Thank you. And whatever I have spoken, it's all written about, and those references are here. Thank you. Yes.
Thank you so very much. Now the floor is open. If you want to ask any question or need any clarification, please feel free. You don't get him often, and what Professor Grobert said about India's unique position in international nuclear trade, what he did not tell is the role that he played in making that possible. So a big round of applause for that single thing. Yeah, so as I said, you don't get such person often. Please feel free. So I have mics here. A couple of volunteers help me with the movement. Yeah, please.
Okay, thank you, sir, for a
Yeah.
very comprehensive lecture and for providing the scenario of energy sector in India and how India can be a developed economy. Maybe we'll be reaching about $30 trillion. That is what is the Niti Aayog's estimate. And you have already provided the energy requirements. And solar energy definitely cannot fulfill that. That you have already pointed out, even all renewable energy sources. And in this year's budget, Nirmala Sitharaman, Finance Minister, has said that they want to promote the small modular reactors. And is it different from that Bharat reactor that you are talking about? And what is the capacity of that? And what is the stage of development of that small modular reactors? And now government is promoting the private sector participation. And so can you educate us on that?
Well, first of all, yes, there are two concepts which Finance Minister spoke about. One, Bharat Small Reactor, and secondly, SMR. Bharat Small Reactor, India started constructing pressurized heavy water reactor of 220 megawatt capacity. I think there are 18 or so of them already operating in the country. And now the thinking is that there will be some incremental improvement in those reactors, which NPCIL feels that they can do in a time of 6 to 9 months or maybe 1 year maximum. Improvements, they are still working on it, but likely improvements will be that, you see, when the electronics keeps on evolving, so one has to make more and more instrumentation and control has to be digitized much more. There can be improvement in containment so that in the case of any accident, there is no leakage of radioactivity outside. And this kind of incremental improvement, it's not any revolutionary change. There will be incremental change and incremental change or evolutionary changes. So they will be ready with fast. And industry has shown interest, whether it is Tata's or Jindal's or railways, all of them want 220 megawatt reactors. They don't want large 700 megawatt reactor. They are looking for 220 megawatt reactor. And that will be offered as a captive power plant to them. The dialogue is going on. What final business model will be, it is not known at the moment, because it will maybe next 6 months or so we'll know that. We'll have clarity on that topic. Coming to SMR, this is a proven design. We don't have to do much. SMR, we are thinking in terms of, again, a reactor of the rating of around somewhere between 200 to 300 megawatt, pressurized water reactor. Why between 200 and 300 megawatt rating? That it requires a forging. The forging press, which is available in India, we don't have a forging press which can give you 1000 megawatt pressurized water reactor. You can get only to 300, up to 300, or maybe a little more than that. So finally, we may zero down between the size between 200 and 300, and this reactor is at the moment on drawing boards. So it will take some time to develop. So we have to develop one unit first, look at its economics, and after its economic viability is proven, then we can move further. It will be indigenous. Only fuel will be importing, but besides this SMR, which is announced by Nirmala Sitharaman in Parliament, there are more revolutionary concepts also. BARC is working on them. One is molten salt breeder reactor, which people call is a chemist's reactor. There's so much of chemistry involved in that. That is also being worked out. And then high temperature gas cooled reactor also is being worked out, but they are futuristic. Yes, yes, please.
Hello.
Yes.
Sir, I have a small question here that we have talked a lot about how the hydrogen can be converted to the electricity. So I wanted to ask you that how the what how suitable it is for your applications, that because what we are listening like the billionaire and the entrepreneur like Elon Musk is calling it to be a fool's technology to develop the electricity, and whereas the air company like an Airbus is claiming that they will be developing completely hydrogen-based engines for the aircrafts by 2035.
Hydrogen to electricity, I said use electrolyzers to convert electricity to hydrogen and use hydrogen wherever necessary for industrial purposes. Then I also said that these processes which involve power to power conversion are not 100% efficient. You can make them more and more efficient, but it will never be 100%. So use electricity directly wherever you can. Now, coming to use in aviation, let us talk of use in surface transport. Surface transport, one method is you use railway tracks, electrify railway tracks. That is something which we have already done quite a bit. And for long distance transport, one proposal, which is already working in one area in the country, is that have what is known as RoRo methodology. RoRo methodology means that a truck comes to railway terminal, rolls on to a wagon, goes to the destination and rolls off. Rolling on and rolling off, this comes RoRo. On the Konkan railway, it is working very well. A truck driver comes to the designated railway platform, truck is loaded and train moves on. This is quite cost effective. This is one method by which one can have long distance transport. Second method is, which is being proposed in Germany, as per regulation in Germany, a truck driver is supposed to have rest every 4 hours. He cannot continuously be driving. So on highways, at frequent intervals, have charging station where trucks are moving, and when he slows down, takes rest after 4 hours, truck is charged, and after he rests, he moves on further. Third, of course, you have hydrogen-based ICNs. But there you have to then, efficiency will be compromised, that will be expensive. In India also there is a talk of hydrogen buses, hydrogen trains, but in my opinion, there will be a loss of efficiency there, and one has to find, is it acceptable from economics point of view. In case of railways, earlier thinking was that electrify those tracks which are having heavy loads. There's certain way the load is calculated. For example, there is a railway line here. If I say in Tamil Nadu, you have a railway line going to Uti from, what is that, Mattupalayam is the thing, and hardly 2-3 trains in a day. So they are justifying electrification expenditure is not okay. Similar railway line in West Bengal going to Darjeeling or between Kalka and Shimla in north, electrification cannot be justified there. But now thinking is that I was talking to some railway officials, they say it's only fancy thinking, but economically it doesn't make sense. So there, that kind of places you can use hydrogen. But coming to aviation and shipping, use of hydrogen will be a must, because battery storage there at the current moment, the both gravimetric density and volumetric density of energy in batteries is not so much that one can think of using them in shipping or in aviation. So two possibilities. One, use hydrogen. Secondly, use ethanol derived from biomass. But the final word, still we do not know what will industrially prove. This is a field which is evolving, so one has to wait and see how things move. Yes, please.
Thank you for the nice talk. I have a very simple question. Uh, in the earlier slides, like beginning of the talk, you talked about the consumption of various energy sources like solar and fuel and in biomass. So regarding the biomass consumption, like there is no regulation on the like consumption of the biomass in our household or some in other activities. So like how do you calculate the consumption of biomass? And it's more confusing because in most of the like households in villages, they use both biogas and biomass for the cooking and other purposes. So how do you calculate accurately?
Many of these are estimates. They can have inaccuracies. Yes, if you are saying that way. The way biomass is used in household, very difficult to estimate its calorific value, what is going on. And another thing which happens in cooking is that the stoves which are used in villages in particular, they are highly inefficient. You are burning wood and most energy is going to environment, not to the vessel which is being used for cooking. Even in urban areas, gas-fired stoves which we use, they are only 35% efficient. 65% goes to the kitchen. That is why kitchen is the really very hot in summertime because 65% of energy is going there. So this will change when we have induction stoves. Kitchen will not be that warm because in case of induction stove, coupling is I think 95% or 90% in that range. So this is I think another point which to be noted that induction stoves are more efficient in this case. So biomass is just an estimate, nothing more than that.
Thanks.
Yes, please.
Namaste, sir. I am not well informed about hydrogen, but I have a question. I believe we need oxidizers to burn hydrogen. And how do we address the issue of getting like mass production of oxidizers? Uh, I think there was some work being done on scramjets which use atmospheric oxygen in some sort of process for oxidizing the fuel. Um, how do we do this in
Hydrogen to electricity conversion can be done in fuel cells. Fuel cells are, you can say, reverse of electrolyzers. And then hydrogen can also be used in internal combustion engines. So both are work in progress. Efficiency and economics are different. So which technology finally wins, we have to wait and see.
what do you believe will win, sir?
Well, this is a difficult question, very difficult question. I really don't have the answer. It depends. You never know. Some young person will come up with some new ideas, new catalysis, and proceed further. So at the moment, we don't know the answer. Yes, there was one question here. Yes, please.
Hello, sir.
Hello.
Am I
Yes,
audible?
please. Yeah, yes.
Yeah. So, sir, since you are from the public policy background, I want to ask that in response to the first question, you mentioned that the fuel would be largely imported, the nuclear fuel. So, in eastern India, we have major ports like Paradip and Kolkata, and again Jharkhand and Meghalaya. These are major uranium deposits in India. So when can we expect a nuclear reactor to come up in eastern India?
Okay. I think this is a question which will take me to political arena. Sites are selected, nuclear sites are selected in a certain fashion. Department of Atomic Energy invites applications from all states who are interested in having a nuclear power plant and tells them to propose sites. which has, where water is available, which are where geology is stable and so on and so forth. So we received those sites. Then there is a site evaluation committee consisting of expert civil engineers and mechanical engineers. They actually go and inspect the site, and those sites which are found suitable, then we proceed further uh, by getting acceptance of the state government and the central government for the sites. In eastern India, a site, Haripur in West Bengal, was selected by this process when left government was in power. Okay, when then government changed, we had a different party in power. They said, no, we don't want any nuclear power plant in West Bengal. So this is, I think, this is the answer. If you want, this is the exact sequence to what has happened. So one is the state government
from West Bengal.
I could see that. So I think now here we are a union of states, so one has to respect what the state chief minister says. And if there's a change in government, again, you don't know, situation may change. But just note one thing, just 200, less than 200 kilometers from the border in West Bengal, in Bangladesh, at Rupert, a nuclear power plant is coming. I will not say anything more. You can now think further. Okay. There's one more. Okay, please, here. Here, this striped T-shirt.
Good evening, sir. I want to ask about the scope and the current status in the development of the photovoltaic technology in India.
Oh, I don't think I'll be able to answer this question, not my field. Sorry. I think some physics person present here may be able to answer better.
Good evening, sir. Sir, my question is that, sir, from the perspective of India, the GDP in R&D is less than 1%. And if we go for the hydrogen fuel and if some other country develop it, they would sell us costly for the hydrogen technology. But if we apply the model of Sweden, where they are electrifying the road, it would cost, it would save a lot of money in the space because India has so much crowded area. So electrifying a road could be a better option. And the technology of electrifying is currently booming in the world. And if India is also on the way to build its semiconductor power plant or chip manufacturing. So what's your opinion on that, and why the country should focus on, from my perspective, in the electric field? How do you see that?
Let us first talk of electrolyzers. Electrolyzer technology has been developed based on indigenous research in India itself. DRC has developed technologies, two different technologies, alkaline cell and other is, I think, copper chloride based high temperature technology. Alkaline cell technologies, to develop it further at a large scale, MOU has been signed with 2 oil companies and larger size plants are being set up. So a good progress has been made there. Similarly, there is a indigenous technology, certain private firms like Reliance, they have signed MOUs with outside countries and acquired outside technology, and they are also going further with the production of electrolyzers in the country. So this, I think that area is under control. With regard to electrifying even a road transport, well, I think as far as railways are concerned, we are electrifying them. Road transport is a bit different. Whatever technologies are being developed in other countries where they are talking about the road, the vehicle is moving on the road, is getting charged, they are still at experimental stage. Currently, India is not thinking in that direction. India is only thinking in terms of electrifying railway tracks and going in for battery operated vehicles. There is some talk about hydrogen cell, using fuel cells based using hydrogen in long distance trucks and buses, but that so far, whatever the results are, they don't look like very that they will have a high efficiency. Again, because there is a two-step conversion involved there. Okay. So there is one more. Okay.
Sir, like as you said that along with renewable energies like solar energy and wind energy, India also needs to use fossil fuels so that it can become a developed country. So, since fossil fuels lead to carbon emission, is there a possibility that of removing that effect by having more forest area?
Yes, for carbon removal, one method is this, you have more forests. Second, you use chemical techniques for carbon capture. You capture carbon from the atmosphere, and either you can combine that with hydrogen to produce chemicals which are used by industry, or we have to produce plastics also, which can be produced by that methodology. Second is plant more forests. So both methods are possible, and we are working on both these things. There are people, chemical engineers, who are extensively advocating the carbon capture and use. They are saying that there are several variety of chemicals which can be produced by that route. And Professor G.D. Yadav, who was Vice Chancellor of Institute of Chemical Technology, is an advocate of that. He has written papers, and so much work has been done by him.
Thank you, sir.
Thank you so much, sir. Please take your seat. Okay, so thank you so much, Professor Grover. We just came to an end of the first session. We have another session. Before we move to the second session, I have a small announcement to make. The students who are receiving their certificates for academic performance must have received emails. I request all of them to please come to the leftmost corner so that it will be easier for you to move and we'll save a lot of time. Please quietly move to the first couple of rows on the left side of that. So moving on, I request Professor H.N. Ghosh to kindly join us at the dais. Quietly move to the first couple of rows. And no one goes out. Huh? I would man the gates. Guys at the gate, you guys are responsible for not letting people go out. Be a part of your friends and colleagues' success. Come on. Just to let you know, on the Foundation Day, we also celebrated our academic performers. So there would be semester toppers, year toppers, different number, but yeah, we will have some time for that. I would request the chief guest, Professor Grover, to give away this academic awards to students. So let me move on to the next session, and we'll start with the subject toppers in each school with the MSc integrated MSc program first. The third semester batch 2022. As I take the names, guys, please come this way. School of Biological Sciences, Catherine Cletus. So she has secured the SGPA of 9.70. So this is the third semester 22 batch. Third semester batch 22 Chemical Sciences, Aradhana Pani. She has a perfect 10 SGPA. third semester, batch 2022, School of Mathematical Sciences, Pragyan Sensova, who has secured SGPA of 9.50. 9.50 in maths assumes quite a lot of significance anyways. For the School of Physical Science, guys, the clapping should not stop. Yeah. For the School of Physical Sciences, third semester, it is Ashlin Thomas with an SGPA of 9.68. For the fifth semester, batch 21, School of Biological Sciences, Amir Alex Paul, SGPA of 9.30. For the School of Chemical Sciences, there is a two-way tie. It's Abhishek S. and Sriram Vignesh AK. Both have registered 9.68 SGPA. For the School of Mathematical Sciences, batch 21, fifth semester, Sandipan Samanta. Sandipan's SGPA is 9.20. Sandipan. For the School of Physical Sciences, fifth semester 2021, it's Priti Priya Das Behra. Priti Priya, yeah. Priti Priya has an GPA of 9.45. Moving on to the seventh semester, batch 2020, School of Biological Sciences, it's Advita Sharma. Advita, oh, she's not there. Then Chemical Sciences, Prayag Ranjan Sahu, has a SGPA of 9.83. School of Mathematical Sciences, seventh semester, it's a tie. Arjab Jogani and Upendra Singh Parmar. Arjab. The School of Physical Sciences is Sajak Kumar. We then move on to the MSc component of integrated MSc PhD program. The subject topics for each school. For semester 3 physics, it's Saurabh Kumar Giri. That's not him. Oh. Semester 1, it's Dhanus, Hani Sai, and oh, that's one. Dhanus, Hani Sai, Ramaraju, Rudra Raju. With an SGPA of 9.4. Is it safe to call DPSR Rudra Raju? Thank you. For semester 3 mathematics, Arijit Mahato. Arijit Mahato has an SGP of 10. Perfect mathematics. For semester 1, it's Ipsita Ghadai. Moving on to chemistry, it's Ipsita Paricha, another Ipsita. Not just another Ipsita, another 10-pointer as well. Staying with chemistry for semester 3, it's Mamata Bhoi. Moving on for semester 3, biology, Miss Muskan Chhatri. Staying with biology, semester 1, it's Miss Hiral Rawal. From subject toppers to semester toppers, integrated MSc program, the first semester batch 2023, it's Josna Anna Sam. The overall semester topper for the batch with an SGPA of 9.77. For the third semester batch 22, it's Aradhana Pani, another 10-pointer. For the fifth semester, there is a tie. Batch 2021, it's Abhishek Ace and Sriram Vignas AK, both with 9.68. Abhishek Ace, Sriram Vignas AK. For the seventh semester, it's Prayag Ranjan Sahu. Seventh semester, Prayag Ranjan Sahu. Semester toppers for CMRP. First semester, it's Sayan Pramanik and Shivans Mahadev, both with an SGPA of 9.7, identical SGPA of 9.79. Sayan wasn't used for some good reason. Semester toppers for integrated MSc PhD. That's Shivans Mahadev, CMRP. For batch 2022, semester 3, it's Arijit Mahato. And Tipsita Paricha, both 10 pointers. 10 pointers के लिए तो पूरा बजना चाहिए. Come on. या फिर खुद लाओ. Overall performance for integrated MSc, it's Ashlyn Thomas. So for a better clarity, it's overall topper for the batch, for the semester, odd semester, across the batch, CGPA. Similarly, overall performance, CGPA, topper in integrated MSc PhD program is Ipsita Paricha. Ipsita will have to do a couple of rounds. From odd semester, we move to the even semesters of 23-24 session. Subject purpose in each school for integrated MSc program. Fourth semester batch 2022 Biological Sciences, Annabelle Anthony Biju. School of Chemical Sciences, there are two, Aradhana Pani again and Devika A, both with an identical SGPA of 9.73. Aradhana Pani. Devika A. Moving on, School of Mathematical Sciences, it's Progyan Sensoa. Again. Progyan has an SGPA of 9.27. Then for physical sciences, Aditya Ashutosh Dash, the hoping SGPA of 9.91. From batch 2022 to 21, sixth semester, subject topper in biology, Samiksha Kar. For chemistry, it's Om Prakash Swai. Samiksha has an SGPA of 9.7. Om Prakash has 9.82. From chemistry to mathematics, sixth semester batch 21, topper is A. Rameshwar Patra with an SGPA of 9.20. School of Physical Sciences, it's Priti Priya Das Behra. Once again, with an SGPA of 9.68. Moving on to the 8th semester, biology, this is a three-way tie. Kallam Tejasvi, Saina Rath, Tanisha Ashwin, all with an identical SGPA of 9.40. Kallam Tejasvi, Saina Rath, Tanisha Aswin. Then Saina and then Tanisha in that order. Moving on for the School of Chemical Sciences, batch 2020, 8th semester, it's Asutosh Panda with an SGPA of 9.8. Asutosh Panda, Chemistry, 8th semester. School of Mathematical Sciences, batch 2020, 8th semester, topper is Arjav Jogani. For Physics, 8th semester, batch 20, Sunandan Panda. Sunandan had an SGPA of 9.80. Moving on to the subject topics in integrated MSc PhD, semester 4 physics, Sarup Kumar Giri again. Sarup Giri was not there. For semester 4 physics, Chinmay Samanta. Semester 2 DPSR Rudra Raju. With an SGPA of 9.2. For semester 2 physics, Srijan Voleti, sorry. Moving on for the semester 4 mathematics, it's Arijit Mahato with an SGPA of 9. And for semester 2, it's Narendra Kumar Sahu with an SGPA of 8.40. Narendra Kumar Sahu for semester 2 mathematics. Moving on for semester 4 chemistry, it's Shreya Mishra. And for semester 2, Barsarani Sahu. Both Shreya and Barsa are 10 pointers. Moving on for semester 4 biology, there are 2 toppers, Muskan Chhatri and Miss Pragya, both with SGP of 9.40. Muskan Chhatri followed by Pragya. Semester 4 biology, subject topper in the program MSc PhD, integrated MSc PhD. Moving on to the second semester biology, it's Miss Hiral Rawal. Semester 2 Biology, Miss Hiral Rawal. Moving on to the semester toppers for integrated MSc program for semester 2, batch 2023. It's Jyotsna Anna Sam once again with an overall SGP of 9.50. For fourth semester, batch 2022, it's Aditya Asutosh Das. For the sixth semester, batch 21, it's Om Prakash Swai. For eighth semester, batch 2020, so two-way tie, Ashutosh Panda and Sunandan Panda. Both with an identical SGP of 9.80. Ashutosh. Moving on to the master's program in medical and radiological physics. Second semester topper is Shivans Mahadev and Sogato Nag, both with an identical SGP of 9.79. For the semester toppers in integrated MSc PhD program, that's Shivans. Shivans, second semester CMRP with an SGP of 9.79. Saugata Nag, second semester 9.79. Guys, please रुक जाओ भाई, कहाँ जा रहे हो? You got that exit? You the पीछे वाला. Semester topper MSc, integrated MSc PhD, chemistry second semester, Shreya Mishra. And semester 2, Barsa Rani Sahu. पीछे से जा रहा है वो, देख क्या रहा है? Shreya Mishra, semester 4 chemistry with a perfect 10. Semester 2, Barsarani Saho, yet another 10-pointer. 3 more segments left. Overall performance CGPA integrated MSc for the event semester 23-24 is Ashlin B. Thomas with an CGPA of 9.70. Similarly, the overall topper in the CMRP is Shivans Mahadev. Shivans Mahadev, overall topper, second semester CMRP, 9.79 CGPA. And the last award of the day for overall performance in the integrated MSc PhD program for the second semester is Ipsita Paricha. So quite rightly, Ipsita becomes the showstopper today. Thank you so much, sir. That brings an end to this next second segment of the day. Now I request Professor Hirendranath Ghosh, Director, NISER, to honor our chief speaker with a small token of appreciation from NISER. that formally brings down the curtains for today's program. And before we leave, give me 10 more seconds. Let me thank Professor Grover for being here with us. Thank you so very much, sir. I remember I was there with Professor Ghosh when he called you, and you immediately said yes without even. I sensed that. So I mean, I can. I don't really think we can thank you enough for this. Thank you so very much once again, and thank you so much for whichever way you guys are on the inside the hall. And please be little disciplined. There is